Hello again. In this video, we're going to work on section 3.4. It's about the eigenvalue method to solve homogeneous first-order linear systems of ODEs. Okay? So, and the basic ingredients to solve homogeneous linear system of ODEs will be the eigenvalues and eigenvectors. Eigenvalues and eigenvectors. These are very important, quite important concepts from linear algebra. I'm gonna review those concepts here, okay? So first of all, let's think of that equation. So we have a vector v, and we multiply that vector with a matrix and obtain another vector, okay? So this is called a linear transformation. A linear transformation transforms the given vector v into another new vector y, okay? But sometimes when I transform one vector, I just get the multiple of that vector. Okay, maybe in the previous case I can say that, okay, let's say this is v vector. Okay, don't do that. Okay, and then let's say when I transform this vector, I get this vector. Okay, so this is a times y. Let's say this is the v vector, and let me make it. It doesn't have to be actually orthogonal, so it can be any vector, maybe like that. Okay. Sorry, I should say AV. Okay. So I take one vector and I multiply that vector with a matrix and obtain another vector, y. Okay. But sometimes when I take a vector v, okay, and when I apply linear transformation on that vector v, I just get a multiple of that vector. Okay, so no, this is not a vector, right? It's a matrix. So when I multiply the v vector with a, I just get a multiple of the v vector. So these transformations are kind of important transformations, and it has many applications everywhere in different sciences. So in such a setting, we call this spatial vector as eigenvectors, and that spatial constant lambda as eigenvalues, okay? And this is only true when, actually, maybe I can look at here. I want to have this situation like a times v equals lambda v, and I can move the lambda v to the left. Av minus lambda v is equal to 0 vector, and I can factor out v on the right. So a minus lambda I v is equal to 0, and this equation has only non-zero solutions if the determinant of a minus lambda I is equal to 0. In other words, if a minus lambda I is not invertible, okay? So the values that satisfies these conditions are eigenvalues, as I said to you, and the vectors, by the way, the non-zero vectors that satisfy this condition here are called eigenvectors. Okay, so they are important, very important concepts. For a 2x2 system, I can say so. AV lambda v is equal to AV is equal to lambda v if and only if a minus lambda I is equal to a minus lambda I times v is equal to 0. And in such a case, eigenvalues are the lambda values such that determinant of a minus lambda I is equal to 0. So we should obtain these lambda values to get the eigenvalues, okay? It's just a matter of calculating determinant, okay? All right. Let's find the eigenvalues of this guy, okay? And remember, to find eigenvalues, we need to know what is determinant of a minus lambda I, and I'm gonna set it equal to 0, right? Maybe I can delete 0 part for now. Determinant of a minus lambda I And by the way, I here is the identity matrix. So maybe for this, normally there is an easy way to write this determinant, but since this is our first attempt, I can write this separately here. A minus lambda I is actually equal to 3 minus 1, 4 minus 2. This is A, right? Minus lambda times I, and I is the identity matrix. Of course, multiplying with lambda means lambda is a constant, right? Lambda is a number. So that's actually equal to 3 minus 1, 4 minus 2, minus 2. Minus. Now multiply each entry in this matrix with lambda. Lambda, 0, 0 lambda. That's why this is actually equal to 3 minus lambda, 0, 3 minus lambda, minus 1 minus 0 is minus 1 again. 4 minus 0 is 4. Minus 2 times lambda, minus 2 minus lambda is minus 2 minus lambda. Okay. All right, cool. So we get what? Oops, sorry. I'm trying to select this, and normally I should be able to do that by, yes. Maybe I can do it again. Almost. Let me do it, try to do it one more time. Come on. Anyway, okay, I am not that again. Anyway, a minus lambda I is this, right? And I want to have the determinant of that equal to 0. So determinant of 3 minus lambda minus 1, 4 minus 2 minus lambda. Remember the determinant of a 2 by 2 matrix, this times that minus this times that, right? 3 minus lambda times minus 2 minus lambda minus 1 times 4. All right, let me FOIL here. 3 times minus 2 is minus 6 minus 3 lambda. Minus lambda times minus 2 is plus 2 lambda. Minus lambda times minus lambda is plus lambda squared. And here minus 1 times 4 is plus 4. So if I simplify that, lambda squared, 2 lambda minus 3 lambda is minus lambda. Minus 6 plus 4 is minus 2. Great. I want to set it equal to 0, right? And find the lambda values that satisfy this equation. And I can factor out this equation, right? Lambda minus 2 plus 1 is equal to 0. Yes. So lambda is equal to 2 and minus 1 are the eigenvalues. Okay? This is how you find the eigenvalues. All right? I hope it is clear for everyone. So let's also find eigenvectors of the same matrix. All right. Find the eigenvectors of the same matrix. So what are the eigenvalues? So let me write down again. Here's lambda minus 2 and 1, right? These are the eigenvalues. And to get the eigenvectors, we need to look at this equation, right? What was that equation? Remember, A minus lambda I times V is equal to 0. That V here will be the eigenvectors, okay, of the corresponding eigenvalue. So let me start with negative 2, okay. For negative 2, what do we get? if I just plug it in -2, I will get a minus, so I will just add 2 to the diagonal entries, right? 5 minus 1, 4. If I add 2 to diagonal entries, it will be 0, right? Yes. And this is v1, v2 is equal to 0, right? It's actually 0 vector. Maybe I can write this also as entries, 0, 0. So basically what I need to do is just solve this equation, right? And this is, maybe I can also write this way. Times that is equal to 0. So basically, to solve this equation, I need to solve this augmented matrix, right? 5 minus 1, 4, 0, 0, 0. And the way to solve this, remember, try to row reduce left-hand side to the identity matrix. So to do so, what should I do here? I can, okay, remember I have to make this entry 1, right? So let's subtract the second row from the first row. So row 1 goes to row 1 minus row 2. It is 1, negative 1, 0, 4, 0, 0. And even actually, okay, maybe I can write down here. Now I have to make this entry 0, right? And how can I do that? Multiply the first row by negative 4 and add it to the second row. So row 2 will be row 2 minus 4 row 1, right? 1, negative 1, 0, 0. And if I multiply this with negative 4, it will be 4, right? 0. And I have to make this entry 1. Okay. So I can just multiply this 1 over 4 and add it to that row. And actually, maybe I can first make this entry 1. So row 2 goes to 1 over 2, row 2. It will be 1 minus 1, 0, 0, 1, 0. Okay, wait a minute. Did I make a mistake here? What are our eigenvalues? Okay, let me go back to the previous page. Look at the eigenvalues again. Eigenvalues are 2 and minus 1. Okay, not minus 2. Okay, I was like, there's something wrong here. So let me go back and change something else. So 2 and minus 1. Sorry, guys. It should be 2 and minus 1. So we're going to change a little bit. This will be 2. Now what I need to do is I need to subtract 2 from both entries on the diagonal, right? To get lambda minus I part. So it will be what? 1 and 1? No. If I subtract 2 from negative 2, it will be minus 4, right? Cool. Okay, so let me change this part either. 1 minus 4. And maybe I can erase all these parts. Okay, so as you see here, it is very important to start with the correct eigenvalue. Otherwise, you will not be able to find the eigenvectors. Okay, so now let's try to solve this equation. So what I need to do is multiply the first row by 4 and add it to the second row. So row 2 will be row 2 plus 4 row 1. Actually, minus 4 row 1, yeah. Minus 4 row 1. I want to cancel this entry, right? So it is 1 minus 1, 0, 0. Yes, now I have reduced this part. Now what I can say here is v1 minus v2 is equal to 0, right? Then that's the only thing I have. There's nothing coming from second row. So which implies that v1 is equal to v2, right? So here v2 is the free variable, right? v1 is depending on v2, but v2 is not depending on anything. So v2 is free variable. And I can write v1, so I can write v as, so v is equal to v1, v2, but I can write v1 with respect to v2, right? With respect to free variable. And I can factor out v2 here. 1, 1. Yes, this 1, 1 vector is our first eigenvector, okay? So 1, 1 is eigenvector of lambda is equal to 2, okay? This is how you find eigenvectors. Similarly, let me try it. Can I fit in here? Maybe I can. Let's see. Let's try to fit in here. Okay, for lambda is equal to -1. Again, just plug the -1 here. If I plug the -1, which means I will just add 1 to the diagonal entries. 4, -1, 4, -1. So I can reduce it to write 4, -1, 0, 0. And I can multiply the first column by 1 over 4. 1 over 4. Sorry, this will be 1 minus 1 over 4, 0, 0. Cool. Now I row reduce it. So what will be the solutions then? In the setup, v1 minus 1 over 4, v2 is equal to 0. And nothing coming from the second column, the second row. So from here, what I get, v1 is equal to 1 over 4 v2. Again, v2 is free. Okay, so I can write the eigenvector then as v1, v2, and v1 is 1 over 4, right? 1 over 4 v2, v2, and I can factor out v2, 1 over 4 comma 0. So this is 1, right? And now, so this implies that this vector here is eigenvector, okay? 1 over 4 minus 1 over 4 comma 1 is eigenvector of lambda is equal to -1, okay? This is how you find eigenvector. All right, I hope it's clear for everyone. So in the next video, I'm going to show how to solve system of differential equations, ODEs, using eigenvalues and eigenvectors. So for now, let me stop here.